thank you all for coming to the inaugural Flower Monthly event. This event has been designed to better connect the flower community together, and provide announcements and provide basically a forum for us to more collectively work on the flower ecosystem. It's wonderful to see you all. My name is Nicholas Lane, and let's give you an agenda of what we're going to see today. We're going to have begin with an overview of what these Flower Monthly events are going to be comprised of. Then we have Daniel. Daniel is going to tell us about the exciting components of Flower 1.2 that was released recently. Then we're going to have Charles talking about a critical component of the flower ecosystem, flower baselines, which enables you to compare other alternative algorithms to your own. We're then going to have a discussion about an exciting new sort of initiative in Flower called Flower Working Groups and Flower Sites. So I'll be explaining what that's all about. We then have an allocated portion of the meeting to involve you more directly in a community discussion and a question and answer session. And then after that, we're going to come to our main event. And so that's going to be an invited talk by Javier Fernandez-Marques. He's a research scientist at Samsung AI. He'll be talking to us about Federated Supernetworks. So it's super exciting stuff. But before we get there, let's talk about why we're here. So this is a new type of meeting that we're introducing into sort of the community. It's called Flower Monthly. This event will be happening every Wednesday, the first Wednesday of the month, and we're going to endeavor to have the time be consistently at 5 p.m. GMT or 9 a.m. Pacific time, so you can kind of get used to this sort of cadence. The aim, as I mentioned earlier, is just a regular, routine, informal sharing of information and providing a forum of discussion so we can better coordinate how the flower ecosystem is building out. We're often going to have invited speakers. Sometimes these folks are going to provide tutorials on how you can get more out of flower, how you can investigate interesting avenues of federated learning and so forth. Other times we're going to see people present pieces of research or interesting pieces of projects that use federated learning applications in some way. This is also going to be a more regular meeting that supplements our annual Flower Summit series with announcements of updates to the framework. We're also going to have updates from flower working groups and flower sites that I'll be defining later for you. But suggestions are completely welcome. So this is an evolving process. So we'd really love to get your feedback as to what should happen in these meetings, because after all, they're really aiming to connect us all. And so if you can communicate to us what you'd like to see in them, we can better grow things together. Now, during this meeting, please feel free to jump onto the Flower Slack workspace. And in particular, we've made a new channel called Flower Monthly. So if you have suggestions, if you want to propose changes or your ideas, please put them in the Flower Monthly channel, and we'll follow up with you, or you can interact with each other to sort of push things forward. So with that bit of a preamble, I'd like to pass the baton to Daniel. And Daniel is going to tell us about the exciting advancements that have been made in Flower 1.2. And so over to you, Daniel.
Daniel,
there we go. Okay. Sorry. Hi, welcome everyone. This is great. We've been wanting to do this for quite a while, and I'm excited that this is finally happening. Let's get started with the latest release of Flower. We don't have that much time, so let's jump right into it. Next slide, please. Flower 1.2 was released fairly recently, and it comes with a whole bunch of improvements, both under the hood and features that you can directly use. we have advanced it in many different areas. We have, for example, a lot better GPU support. It's still not where we want it to be exactly. We're still working with some of the underlying libraries that we use under the hood to improve GPU support in simulation, for example. We have updated Jupyter notebooks to show how to use GPU support, for example, on Google Colab. We have a brand new example with federated analytics that shows not to do federated learning, but really federated analytics with Flower and Pandas. And we have a blog post about that. We have new strategies like Crum and Multicrum, updated a whole bunch of other things. We have a Flower baseline with fed averaging and MNIST that we're going to hear about later. And we have the driver API, which is highly experimental. And today I want to talk about the driver API. Next slide, please. So the driver API is really something that we've been thinking about for quite a while, and we have a lot of feature requests and also things that we want to do, ideas how we want to make the framework better. Next slide, please. And one of those things is async-FL. Next slide, please. For example, give users a way to implement FatBuff in a way that's easier than it is today with the strategies that we have. Next slide, please. Multi-tenancy is another one. So having a server that we can keep running and then having multiple workloads that use that server, use the very same fleet to execute their workloads. Next slide, please. I have too many slides today. Another thing, especially important for researchers, is a way to build custom FL loops. Basically, not being tied to what the strategy API offers you, but really writing a custom for loop and doing whatever you want to do with the fleet. Next slide, please. Then deployment is another big one, giving users a way to deploy Flower in a different way, in a way that makes it just easier to deploy it and keep the Flower server running. Next slide, please. Related to that is an admin API that makes it easier to basically administer the running Flower system. Next slide, please. And the last one, probably maybe not even the last one, but these are just a whole bunch of ideas that are all basically converging into the Flower API, is a modular way to provide secure aggregation, not just one or two or three built-in ways to do secure aggregation, but really a framework for both researchers and practitioners to build also new federated secure aggregation approaches on top. Next slide, please. And with that, I want to go into a quick live demo. Let's see how this works here. I will share my screen now. Sharing the full screen. Okay, you should be able to see my screen now. Yeah?
Yes. Mm-hmm.
Good. So we have in the middle, these are a lot of terminal windows, but here in the middle, bear with me, we have the Flower server. And we're starting the Flower server now. On the right-hand side, we have three terminal windows there to simulate three clients. On the left-hand side, we have two terminal windows there to simulate two workloads. We call them workloads. It's basically what currently the strategy and the loop that drives the strategy are. So in the current execution model of Flower, you call start server, and that repeatedly calls the strategy, and the strategy then configures the workload and aggregates results and a couple of other things. And all of this is basically happening here, not inside the Flower server anymore, but really outside in order to enable us to run multiple workloads concurrently. So the Flower server is already running. Let's connect the first client to it. Let's connect the second client. And then finally, let's connect the third client. And with that, we can start the first workload. Over here, we can see that something starts to happen on these clients. We can see the logs on the server side. And the fantastic thing, the thing that has not been possible up until now, is that now we can also start a second workload that uses that server and that federation of clients and also schedules tasks while the other one is running. So this will probably run for a few more seconds until it's done. There's a last round that is happening right now. So now both workloads are finished. The server just keeps running. The clients just keep running. And one of the additional new features that we have, or something that is just now possible through the driver API, we can just start the workload again. And yeah, we can keep the server running. This is something that, especially for production deployments, I think this is going to be a huge step that will make it a lot easier to keep a Flower server running and to deploy Flower in a production setting. The Flower server could now be bundled in a Docker container, store it somewhere, and you can just keep it running as a process. And then data scientists that want to work with the system, that want to schedule workloads across this fleet of clients, they can just go ahead and start their workloads separately from the running Flower server that manages the connection to the Flower clients. And that's already it for the live demo. Let's get back to slides, please. Next slide. The driver API, as I said in the beginning, is highly experimental, so don't use it. Next slide. If you need stability, if you need API stability, that is. We are still iterating on the kinds of messages that get exchanged between, especially the workloads and the server. We're iterating on also even some of the semantics of the API. It's usable, it's available in Flower 1.2, but we're not making any compatibility and stability promises yet. This is a highly experimental thing. We would love to get your feedback on it. So next slide. If you want to use it, if you're curious, and if you are not mad if you change any of the APIs in the future, feel free to check out the mt-pytorch code example. That's basically just a code that I've been showing just now. Next slide. I think I'm already at the end.
Exactly. Wow.
Yeah,
Well,
with
Daniel,
that. Oh yeah, sorry, Nick, go ahead.
I was going to say that was amazing. Thank you for the demonstration and the summary of Flower 1.2. It's very cool. I didn't mean to step on your end of the talk there.
No, it's good.
Okay, great. So thank you, Daniel. We're going to move next to Charles. Charles, if you've been following the GitHub of Flower, has been working up a storm of updates and commits and so on. And he's been working, one of the things he's been working on is Flower baselines. And so I'll hand over to Charles to tell us all about Flower baselines. I think it's going to change your life.
Yeah, hi everyone. So I'll quickly go over the baselines, what they are and what they entail. So maybe you can go to the next slide. The gist of baselines is to implement with Flower experiments from popular FL papers. So for instance, here we have a publication. This is actually the Fed average paper from 2017. And from this paper, if you can go to the next slide, we have the following experiments as an example inside the paper. So MNIST, CIFAR, Shakespeare, which are just tasks using a specific data set and a specific model. And from these different experiments, we're going to create some Flower implementations, and that's what we're going to call baselines. If you can go to the next slide. So here you go. And those are separate baselines that people will be able to use. And the great thing about baselines is that it gives a very quick overview of a paper, of the implementation, and how you can just go from a specific task to a working example with Flower. And if you can go to the next slide. This is all under the umbrella of the FL Starter Pack, which is something we're trying to, an initiative we're trying to launch. The idea behind this is to provide the community with a set of data sets, so popular data sets that are often used in academia, and also to provide methods for partitioning that allows us to adapt them to the FL settings. Also to provide models, so standard models for different tasks that will work with those data sets. And then using the strategies already implemented in Flower, we will be able to create the baselines with those elements just put together. So for instance, as I talked about earlier, the Fed-average paper, we can just take the dataset from MNIST and then the CNN model that we want, and we will be able to implement the experiment very quickly using Flower. This in turn allows us to not only be useful for newcomers, that maybe it will help them to better understand papers, to have the implementation with Flower alongside. It's going to be very easily implemented, but also for people who read a lot of papers and who want to try and implement different architectures and maybe tweak them also. So this really is for everyone. And if you can go to the next slide. We have already started, I think this was 2 weeks ago, something like this. We released, so, well, Fed-average with MNIST using CNN. We wanted to first release this baseline, as it is kind of the pioneering paper for FL that described the federated learning that we're used to today, and introduce the Fed-average method that's widely used in FL. And maybe if you can go to the next slide. Here you see the results that we got when trying to replicate the paper using the same parameters, the same architecture and the data set. So we're very happy with those. And the idea is to provide for as many experiments as we can, to provide similar results, to be able to replicate them using Flower. And the next one we're going to implement is, you can change the slide. So it's going to be FedProx, also with MNIST and with the same CNN actually. This should be released probably next week. And the idea behind FedProx is to provide a regularization term for the federated setting to achieve a better convergence when different devices don't have the same performance. And yeah, that's about it. I don't know if you have any questions about baselines.
This is a really important new feature of Flower. So yeah, feel free to ask a couple of questions now if you're online.
Maybe on the Slack also, don't hesitate to send messages.
Sure. We
I have one question.
Yes, please, Javier.
So, do you have any plans on supporting other baselines beyond, image models? Something working with audio, maybe, or text?
Yeah, this is actually one of the planned baseline. That's going to be the Shakespeare, so with LSTM described in the Fed-average paper. this is one of the top priority baselines we want to implement. And also maybe something important to point out is that currently the structure of the project is not, we don't yet have like a folder full of data sets and folder full of models, but as we will build upon baselines, once we have enough, we will be able to separate them and to make it easier for everyone to also implement their own baselines.
Thank you.
We'd love to see some contributions from people if they'd like to particularly take their own work and contribute to the framework and let other people easily build on top of their work, compare to it, and so on. I think one of the reasons why baselines is so important, it's so exciting to us, is that it's going to transform FL research and its ability to compare and scientifically contrast these methods and with reproducible methods. So it's a very important step. Okay, so thank you, Charles. Thanks very much. Our the next phase of this month's Flower Monthly would be to lay out for you 2 proposals. We have 2 particular types of initiatives that we want to kickstart within Flower. One is called working groups, and one is called sites. So Flower working groups and Flower sites. What I'm going to endeavor to do in the next 10 minutes is just briefly sketch out to you our provisional ideas of what working groups and sites are going to be. We'd love to get your feedback to see how we can refine these ideas further. But these are driving towards more connective experiences for you as a community with the Flower ecosystem. And so let's talk first about Flower working groups. In a nutshell, a Flower working group, as we currently envision it, is a working group will be a community members who want to come together to define, manage, and build out a particular part of the Flower ecosystem that they're really passionate about. And so we envision this to be an organic process whereby people propose working groups. We facilitate the coordination and establishment of these working groups. We perhaps bring people together who have common interests so that then these working groups can flourish. So example working groups that we'd like to propose, just to kind of kickstart your own thinking, would be things like healthcare or support for mobile clients. If you're familiar with other open source communities, they also have this notion of working groups. And so we'll try to tightly model our idea of working groups similar to these, where community members build out a particular aspect from the core source code. We would expect working groups to likely have sort of a loose structure, whereby there'll be some defined goals of what they're trying to achieve. There'll be some regular meetings defined by the community of people who are working together on this particular feature or area, where they'll meet, get together, and there'll be some timelines. And what we imagine to be the case is that working groups, once they're established, will meet to report their progress or announcements in terms of features and so on at venues like the Flower Monthly event. They'll also produce updates that would appear on the Flower website. 2 key features that we want to point out are that working groups will need a coordinator or maybe multiple coordinators to kind of coalesce the energy of a working group, so it kind of to focus it towards the goals that they want to achieve. And I'd like to make is that if this sounds interesting to you, if you want to see a working group in a particular topic area, please join the Flower Monthly Slack channel, start proposing ideas, and we'll help facilitate the construction of some of these working groups. And to seed your sort of thinking, here are some initial proposals that we came up with of what working groups might get established. One working group, for example, we'd like to see formed is in the area of differential privacy and segregation. Another would be specific domains like healthcare, perhaps finance, or other types of application domains of FL. Baselines is something that we've started ourselves, but we want to involve much more the community. And so that is a likely candidate to evolve into being a working group. Also mobile clients. Mobile clients are quite a time-consuming endeavor because the iOS and Android are constantly changing. And so mobile clients is one, data sets is another. So a working group targeting the onboarding and proper support of various data sets is important. And the final example I'll give is that of speech recognition. It's a particular application domain that benefits a lot from federated learning. And so we imagine a working group such as such as speech recognition being a likely proposal. But again, if you have suggestions, you probably have ideas that we have never thought of, please engage on the channel to get this working groups that you'd like to see underway. The next community proposal that we've come up with is something that we call flower sites. And so unlike working groups, we have this idea of a flower site being, again, a coming together of people who share perhaps a geographic or organizational based sort of commonality, where there's a critical mass of flower users who want to self-organize to better coordinate, offer each other help, and share resources so they can work together on the flower framework. So an example could be a university research lab where a lot of folks are interested in using flower and they want to come together to form a group so they can share knowledge between themselves and organize. Another example would be employees within the same organization or members of an NGO. I think the key difference with a working group is that a site, and this is a either geographic or logically related site, doesn't have to have necessarily a common technical aim or theme. It's just people who are related together who want to sort of work together. And by forming a site, you're going to enable us to better target assistance for you, because a lot of these people within the same organization or the same location would have common issues. And then we foresee that sites, so flower sites, will have opportunities to share updates, maybe share a project that they've all been working on in venues such as the Flower Monthly, and also having this information put on the Flower website. Flower sites will also need a coordinator, maybe more than one, who are willing to organize these things. And finally, so if you want to establish a flower site, if this seems appealing to you, please reach out and contact us, and we'll endeavor to help facilitate the construction of a flower site. And finally, help us refine these two ideas. These are initial ideas that we have in mind to help connect better with the community. You might have a completely other type of vector that you want us to kind of start inside the community. So please feel free to give us feedback so we can refine these ideas. And so we're going to conclude our first Flower Monthly meeting with our first invited speaker. He is Dr. Javier Fernandez-Marques. He is a research scientist at Samsung AI. Javier has worked at Samsung now for about 1.5 years, where he joined with a PhD from Oxford. He's got interests ranging from model compression, co-design, AutoML, and also federated learning. And so today he's going to be telling us about a pretty important, I think, idea in the world of federated learning that he's dubbed Federated Supernetworks. And so with that as an introduction, I'm going to hand over to Javier, who can tell us all about it. Thank you, Javier, again, for finding time to spend with us.
Thank you for the introduction, Nick. I'm going to be presenting mainly one of the recent work I've done here in Samsung AI with other collaborators about federated supernetworks. And later at the end, I think I'll have time to talk about just two small, but ways I like to work when I do simulation with Flower, which I think is quite interesting. Okay, so first, I would like to spend a couple of slides just doing a recap on how federated learning works. So we are at the same point and we understand what the problem we are addressing is. So in FL, normally there is a central and we have different users. Each of them, they own their own data and the data stays with the clients, right? At the beginning of a round, the server will sample some clients, not all of them. And the server will communicate the model we are trying to train in a federated manner. So these clients will do some local training, maybe a few epochs, or maybe just one. After they send their locally updated models back to the server aggregates them, and a new global model state is generated. And we repeat this process for a number of rounds, which is hyperparameter. This is a very simple view of the federated learning process, because in reality, every user has its own data. Some users have different data. In this case of this user, it has a high-end phone. Other users might have like a lower-end phone and use many other devices, so they generate more data. Other users might use a completely different set of devices, in this case, like smart appliances, and generate even more data. And we can start to see here some elements that are heterogeneous. Like, for example, we have data heterogeneity. Data is different from different modalities, maybe different amounts. And we see as well system heterogeneity, right? Like if my models are going to be trained on each person's device, we can see that we have devices that are very capable, like the smartphone, on very compute constrained, for example, earbuds or a smartwatch. So these are the two big challenges that almost all cross-device federated learning pipelines have to deal with, especially if they want to deploy them for real. So what does it mean to have system heterogeneity? So it means that we have devices with different capabilities, maybe from different generations. And if we don't handle this properly, we can have some devices slowing down the process. Because, for example, if we are doing synchronous FL, some devices might take much longer than others to finish their round. If we have different type of data, and this might create, like some devices might not have all the classes in our data set, or maybe there are big distribution shifts, because even if the same labels are present in all people's local data, maybe they have maybe they are slightly different. For example, you can think of self-driving cars, for example. When you attach a camera in front of your car, all the images or frames you would extract look kind of different, kind of similar, but some of them are taken in the night and others during the day. So that's a distribution shift we can handle. But in the work I'm going to be talking about, we primarily focus on the first problem, which is addressing the system level heterogeneity that arises when you have very different devices. And this is a work, this work results in a framework and was developed by two amazing researchers here at Samsung AI, Stefanos Laskaridis and Lucas Duciak. As we have seen in the same federated learning round, we have devices from different capabilities, right? We have high-end phones, and what does it mean to be a high-end phone? So you have a lot of memory, you can process a given workload relatively fast, you have different type of hardware, like you have maybe even an NPU. When we are talking about maybe mid-tier devices, one good example could be a Raspberry Pi, which has an average amount of memory, maybe 4 gigabytes, but is slower in general. And even though it has a GPU, it's a very modest GPU. And on the other side of the spectrum, we have microcontrollers, which almost have no memory. For example, they might have less than 1 megabyte of memory. They have very small throughput, so every model will have a hard time to run very fast. And usually they are even single-threaded. So you can only run workload, and that has to be super well optimized for that particular hardware. And basically throughout the years, we have been able to very well design network architectures that are very well suited to all this type of hardware. and we know how to do it very well for different applications, even microcontrollers. But then the problem is that if we want to federate these very different models, for example, they send the update to the server, we know that these models are so different that we cannot just take an average of them, right? We have layers have different shapes, tensors have different shapes. If you try to do the addition, well, it's gonna result in an error. There are workarounds to handle this in the server. For example, you can do distillation. There are other techniques, but those also make of other assumptions. Like, for example, you have another data set in the server that you can use for distillation, which might not be possible in all cases. So in our solution involves creating a supernet. And what I'm going to do now is to explain a bit what a supernet is and why it is indeed a good solution. So a supernet, you can think of it to be like a regular neural network. But every node you see here, instead of being just one weight, it represents one type of layer. For example, each of these dots will be different type of layer that might have different footprints. For example, depth-wise layer might have very few parameters in comparison with a, for example, 5x5 layer. And all these different layers, when you stack them together, you build a supernet. And the way to extract a standard model out of the supernet is by sampling one operator in every layer of your supernet. So for example, if I have a high-end phone, I can afford sampling very computational and memory intensive layers. So I would sample, as you can see here, the red path. And if I extract that results on the model you see right under the phone. If, on the other hand, I have a very constrained device, like the microcontroller, I can sample other paths, and it will result on which is the green path, and it will result in a much smaller model. What's the benefit of this setting instead of having completely independent and isolated models, as we saw before? Well, the difference now is that every device participating in FL will receive the supernet, and they can decide which path to sample. And depending on the path they sample, they will update those weights, but still those weights are embedded in this model, which is a supernet that is common to every device, regardless of the capabilities of the device. And because every device is sending back this big supernet, there is no problem of shape mismatch in the tensors. So you can proceed with your, for example, your regular strategies like Fed average, or you can propose your own, which is what we did, as we'll see next, to better handle the unique aspects that happen when you work with a supernet. So with the supernet, we have fixed the problem of aggregating, which is one of the big limitations you couldn't do before. And what I'm going to show now is what are the main stages in the Federa's pipeline that enables the learning of the supernet in a federated fashion. So the supernet is like our global model that lives in the server, and we initialize it randomly, like you can do with Flower. And then at the beginning of every training, of every round, what we do is, instead of sending supernet, which can be very, very big, we sample this supernet. And we sample it based on a budget, a communication budget. And we say, for example, I want my sampled supernet to be less than 20 million parameters, for example. So only some of the operators in every layer will be sent to the clients. For example, in this diagram above, we have two clients. One is a Raspberry Pi, one a microcontroller. And you can see they receive a supernet, but some of the paths are like with a dashed line. That means that we didn't communicate that operator because we wanted to save on communication costs. But still, the clients still have a sub-supernet that they can sample based on their compute capabilities. And because the clients themselves know what are their budget, for example, a Raspberry Pi will have a higher budget than a microcontroller, they take samples accordingly. And the way we implement it is that for every batch of training, the client one path randomly. So over the course of several local epochs, we can guarantee that there is a fair good coverage of all the coverage of all the paths that can be sampled by that client. And then, well, the locally updated supernets are sent back to the server. Here, we make a slight modification to Fed average, and instead of in the average of every operator in every layer of the supernet, we keep track of which ones have been sampled in order to weight them accordingly. Because, for example, if the microcontroller here is super constrained, it might only be sampling, let's say, one operator in the layer all the time. So we might want to give it more weight to that update than to another operator that might be sampled only once. And once after aggregation, everything is used to update the global supernet that is still in the server, and the round ends, and we continue with the next round. This, which is like the main contribution of our work, is just one of the stages in our pipeline. And why do we need other stages? One of the reasons is because we are working with a supernet, and in this supernet, for example, for ResNet 18, the moment we have, you can imagine 7 operators per layer, and we have maybe 10 or 16 layers, you end up with many, many paths. Every path represents some model. So we need to search for the best models in the supernet. And these models, the good thing is that they are already pre-trained because we have been training this supernet. So in stage 2, we do the search in a per tier fashion. So we say, okay, which is the best path that has this particular footprint, for example, more than 500 megaflops, but less than 1 gigaflop. So we sample of those, we take the best, and we say, okay, this is the model for a high-end device. And we repeat the same for other tiers. Extract this path. This can be treated in a normal federated learning setting, where there is only one model that only devices of that tier can keep training, for example. And that's what we presented in Fedoras, which is the current state of the art for tier-aware federated learning. One of the big benefits we have here is that because there is this knowledge sharing happening through the supernet, very constrained devices can still benefit from the higher quality training done by higher capacity clients or more powerful clients. And the other way around. Normally, maybe you have only very few very powerful clients, but many, many very constrained clients. So as we will see in the next diagram, that's also a big problem, because if very powerful clients, there are very few powerful clients, they might not be able to have enough data to train a model that is as good as you would expect from a device of that capability. And that's what we're going to see in this diagram. So here what I have represents different models, and the x-axis represents computational footprint. So the bigger the computational footprint, which is measured here in flops, you would expect the better the performance of the model. So bigger models will be towards the right of the plot, and they do perform better than those that are towards the left, which are more constrained. So when all models can be trained on all clients, this holds. You can see that a bigger model works better. But the reality is that maybe bigger models cannot be trained everywhere. For example, here, models that are tier 4, we say that can only be trained on 25% of the clients. Because of this, these models are only exposed to 25% of the data. So they perform very poorly compared to much smaller models that have access to, that can be trained in all clients. And we call this the client participation gap that we can solve with Fedoras thanks to the supernet, because even though some paths in our supernet can only be trained by big clients, those same operators might have already also been updated by other clients, much smaller. So in the end, everything in the supernet has the possibility of being updated by all clients. And I think that's what I wanted to share about Fedras. I don't know if anyone has some questions or comments about this before I jump into some other topic, like just some tricks I have to share. I think could be interesting.
Yeah, I think this is a good point for people to ask questions about this particular Fedora's system before you move on. So anybody out there want to ask questions?
Yeah, I mean, I have tons of questions. This is exciting. You're saying that one of the lower end clients, they can basically sample among a subset of the operators to decide which ones they want to trade.
Yes.
If you have a model like you mentioned ResNet 18, you have quite a few layers. Does this mean that one of the operators in each layer that the client can sample from is just identity to basically make the model smaller on that client?
Yes, you are 100% correct. So in every layer of the supernet, you can have operators you want, but one has to be the identity, because it can be that, oh, this very constrained client samples, and we also make it randomly, the order you use to sample, because it can happen that, let's say, first layer of the supernet, you are already close to exceeding the budget your client has in terms of compute. Then that would mean that the following layers all have to be identity, so you don't add up more complexity. So yes, you're right. Every layer has the option to be identity, so no op.
Makes sense. And then in a have you quantified the contributions sort of to the global model that are coming from individual clients? Can you see whether the more powerful clients, maybe do they contribute more to the overall model than the smaller ones?
Good question. Thing is that I think that we wanted to make an experiment like that to further motivate the supernet, not only from the system perspective, but also this kind of better quality of training for bigger models. But we aren't sure what's the right experiment for this, because the thing is that, okay, bigger quality clients will sample some paths that cannot be sampled by other clients. But then at the same time, those exact paths are only trained by these bigger clients. So in a way they are, I'm not going to say doomed, but it's difficult to show them in isolation that they are better.
It's quite interesting. I have so many ideas about this. This is pretty exciting.
Thanks.
I had one question, Javier, which was, I'm sure you have a good answer to this, but do we only have to run this once to learn a particular great subnetwork for certain configurations? Or is this something, or once or a relatively few number of times for the number of kind of canonical configurations you might encounter of like low end and high end and so on? Or do you envision this, or is there a strong need to run this for every particular federation out there to adapt to its unique characteristics?
Yeah, good question. So as long we don't need to run it more times. So for example, from the supernet, we can say, oh, originally I only did the training assuming 4 tiers that evenly split the spectrum, for example, like we see in this plot, which is actually what we did in our experiment. If later, let's say, oh no, we want to split tier 4 into 3 more tiers, we wouldn't need to retrain the supernet. We will be already in a good position to find the path find the best model in the supernet, within the supernet for that particular new tier. And then we can fine tune it if we want with additional rounds of normal federated learning, and that would be fine. The problem will come if, for example, now that is not, for example, a model that is 2000 gigaflops, 2 gigaflops. does not consider in our supernet. So we will likely need to do some retraining of the supernet. Yeah.
Cool. Very interesting. Other questions from the audience? Well, I think we could
say a few words. Sorry, just a quick one. Can you say a few words how you did the data partitioning? Like, did the smaller clients did you put more data on there, or yeah?
So for CIFAR, we split this evenly. For other datasets, speech commands, I think we put 80% of the data in the smallest, almost nothing in tier 2 and 3, and the remaining to tier 4. So we did try different distributions. Also because we wanted, one of the things we wanted to verify is the scenario where you have many more small tier devices and only some of the big, only very few big devices. Can these big devices still perform decently well? And we saw it was the case. Good question.
Thank you. Maybe to the others, you can also just drop a question in the chat. Yeah.
Okay, so yeah, Javier, please feel free to continue to the next part of the talk.
Yes. Yeah, the next part is quite brief. I put together a repo very recently, like today. Now it's public, so you can find it there under my GitHub. And the idea is I wanted to share two ways of working with Flower that I find them very useful, especially when you want to have many different types of data sets inside your repo that might require different configurations, for example, right? Like different data documentations if you work with speech versus images, a completely different type of models, and things like that. And also I will show how, well, maybe a lot of people know, but to explain the way I do it, the way to scale the Flower simulations. So the first part is a configuration library that is very powerful, developed by Lucas, one of my co-authors in the Federated paper, that we very recently open sourced in Samsung, which is called Awesome YAML. And if you have worked with other YAML config files, most of the way Awesome YAML works will look very familiar to you. But there is one or two features that I think that makes Awesome YAML is super powerful and much more powerful than normal YAML files. And the thing here is as follows. And normally in FL you would start with a base config file, like maybe you have your CIFAR 10 example and you are very happy with it, but then you decide, okay, now I want to consider not only this simple model, but I want a version 18, and I want also a transformer, for example. So one way of doing it is you go to your input arguments, parse, add argument, and then you need to add a new flag, things like that. And then you go to your client and you say, if model name equals ResNet 18, this code is ResNet 50, this other code. So that is fine for when you want like one option or the other, but the moment you want more options, things get completely out of control. So one way of solving it very easily with Awesome YAML is through configurations that allow you to specify how objects are being constructed directly in the config file. So for example, what I'm going to do, I'm going to share my VS Code. I think it should be here. For example, let me just go, I'm going to make this a bit bigger. So here is my base config file that is something that is very standard. And well, by the way, something I haven't said is that this code is exactly the same as the Flower simulation example, but I have changed it slightly so it works with this Awesome YAML library. So let's look at this first. So we have our model, and then there is a property that we call build, and this is a bind node, which means that it's going to build an object, it's going to build it, which is this object. It's going to build it only when you tell it to do so in the code. So for example, if we go to source models.net, that is source model, my file, and then .NET is here. So this is the standard model we have in the flower simulation example. And okay, I have this here. How does it work? So for example, if I have my standard flower client, I'm passing a new argument, which is a config, which in this case is this config. And I will say, oh, config.model.build, and you call it, and this will be equivalent to if you were, here importing from models, import.net, and here you just put .NET. That would be equivalent. Let's say if we want to do something a bit more sophisticated, for example, let's say we want to consider a new optimizer. We could have what I said before. If optimizer name equals SGD, do this. Atom, do that. But with awesome YAML, you can make in a much cleaner and I would say versatile way. For example, in this case, you can see the config.optim is calling something.
I don't understand. I see the.
Oh, sorry. And then what is doing this config optim is coming here. It has the client config and is instantiating torch optim SGD with these hyperparameters. But we know that when we instantiate our optimizer, it still needs you to pass the parameters. So you can still do that in the code. And the thing is that this process is common to all optimizers. So we can leave that there. Let's say now I want to change this. I don't want SGD. I want to try. So you can do a new config, for example, like this one that inherits from your base config, and you only change that node in the config that has to do with the optimizer base atom and a new learning rate. And this config runs everything exactly as your base config with only this change. Only the atom optimizer in the client has been changed. And you can imagine how this can be extended to different situations. For example, let's say now I don't want my tiny model we saw here of in nets. I want a ResNet 18, which is a very common baseline model. You can do this through a config. Again, to rewrite everything, you just you rewrite what needs to be changed from the base. And similarly with other nodes. For example, here we have a bigger model. Maybe we want to use GPUs, whereas before we were only using CPU to train the clients. So this is one of the things I wanted to share. Library is it's super versatile, and I now use it everywhere. So if someone sometimes struggles with config files or things get out of control with hundreds of config files, I think this is could be one solution. The other thing I wanted to share is flower simulation. I think most of you or all of you know that there is this, you can run flower like for real with real devices, or you can run it in simulation mode, which might be more appropriate if you want to just run large-scale experiments. And that works right out of the box. What I want to show in these slides is how you can run the simulation, not in just a single computer, but in multiple computers that are in the same network. And the process is actually super easy. So you need to meet two conditions. One is that all the nodes have to be visible to each other. They have to be in the same network. And the other one is that every node has to have exactly the same Python version and the same repository, like your repo, your code, and your environment has to be the same. And then you would, for example, go to whichever node you want it to be the head of the node, and you type the command you see there, restart --head, and it will print something automatically for you. And you will see some steps there, which I have put in a red rectangle. To connect this RAID runtime to another, run this command. So you will go to another node, type the command, I'm doing it there, press enter, and then you can completely forget about that node. You don't need to run anything at all. Everything will be done for you under the hood. Then you go back to the head node, and you can write, for example, ray status. And if you do so, you will see a summary of all your resources. In this case, I can see I have 2 nodes. And because I ran this onto 8 GPUs, I can see that the total I have is 16 GPUs, which is expected. Okay, now we have created this ray cluster, which is what Flower the hood function. How can I make all my clients to be distributed to all the GPUs in this setup? So you would just launch your experiment as normal from the head node. So you will go Python main.py, blah, 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 and Flower will schedule the clients wherever there are free resources. And this depends on the resources. You are telling your clients that depending on the resources Flower thinks the clients need. In the example I have put together in the repo, you do this by, so you have to do the ray start head, the ray start, and then passing the IP from a node. But at the end, you can run this example just passing -- attach, and everything will be done for you. So I think this is one of the great features in Flower simulation, that you can scale very easily to multiple machines. And these machines, they don't have to be GPU machines. They can be anything. You can have your laptop and another desktop you have at home. That will work as well. So yeah, I recommend to everyone to give it a go. And if you have any questions about this, just feel free to reach out to me or anyone in the Flower channel, I think. And this is everything.
Thank you, Javier. This is amazing. I really love this secret sauce you shared with us at the end of what makes your experiments possible, or just very easy to run. So you literally focus on the science. So very cool. After this first successful inaugural Flower Monthly, we will be back again 1 month from now. And so unless I screwed up, it'll be Wednesday, March the 1st. It'll be at 5 p.m. GMT or 9 a.m. Pacific. I'd encourage you to check out Flower Monthly. This link at the bottom there. You'll see content that is generated out of these Flower Monthly events. For feedback, what have you thought of this event? How you want to see it evolve? It's really in your hands. We want to be guided by the community because that's sort of the ethos of Flower. So tell us what you think. In particular, propose ideas for working groups, propose ideas for Flower sites. We'll have some proper documentation about these, a bit more refined on the website in time. But don't wait for us. Start proposing things and we're going to help you make it happen. Join the Slack working space if you haven't. The URL is also there. And then finally, follow us on Twitter so you can get a steady stream of FL breakthroughs and Flower-based methods to make them happen. So I guess with that, I'd say thank you very much for everyone who joined today. It's been great meeting you all. Any final words, Daniel?
Yeah, thanks everyone. We're pretty happy that we finally got a chance to do this, and we look forward to the next event. Tell everyone about it. Follow FLWR Labs on Twitter, and see you in a month.
See you all later. See you in a month. Take care. Bye-bye.
See ya.
See you.
Bye.
Thank you.
Thanks.
Bye.